Today we're solving problem 21 from the AMC 10A of 2022. A bowl is formed by attaching 4 regular hexagons of side length 1 to a square of side length 1. The edges of the adjacent hexagons coincide as shown in the figure right here. What is the area of the octagon obtained by joining the top 8 vertices of the 4 hexagons situated on the rim of the bowl? Alright, so basically all we need to do is just realize what we are given here. These are regular hexagons, and usually regular hexagons have the same angle measures. So this means that, let's just say this angle is 120 degrees. That means this angle is also 120 degrees. We are also given that each of these side lengths are 1. Well, they're all side length of 1. So let's just do 120. Now, there's this interesting rule where that you can actually construct an equilateral triangle from this regular rectangle here. So, yeah, like so. Right there. This is an equilateral triangle. It might not look that good, probably because it's 3D and not drawn to scale, but this is an equilateral triangle where each angle measure is 60 degrees. 60 degrees. 60 degrees. So by using the same logic, we can construct another triangle here. So from about that point to here, and this is still an equilateral triangle here. Now, from this here formed, this here has to be a right angle because they're being joined together. This is also like an equilateral triangle. And this is where the one thing kicks in. So this side length is 1. And this is part of this equilateral triangle, so that means all of the side lengths are 1. This is 1. So that means this side length is 1 and this side length is 1. So we see here that this is 1 and this is 1. That is an isosceles triangle. So therefore, these two angle measures have to be the same. So they are 45 degrees. 45 degrees each. 45 degrees. Now, according to the Pythagorean theorem, we can find the length of the hypotenuse of this isosceles triangle. 1 squared plus 1 squared is square root of 2. And that applies to everything we have here on this side. So we can construct a triangle here like this, triangle there like this, and a triangle there. Now, what I'd like to do here is we can just flip this up to make it essentially a square. So let's do that. So here. That's not very square-like, but see. So we construct this square here. This square here, and basically we have to draw this octagon, I think. Yeah. So it looks something like this. Now, what we figured out is that this hypotenuse length is square root 2, and that applies to every single hypotenuse here. Square root 2, sorry. So this is not drawn to scale. Oh yeah, not drawn to scale, but you can just imagine it as if it was drawn to scale. Earlier we proved that this side length is 1 and this side length is 1. So this is essentially a square. Each side length is 3, so 3 squared is 9. 9 is the area of the whole square, but now all we need to do to find the area of this octagon is subtract the area of the triangles. The area of the triangles is 1/2 times 1 times 1, which is 1 squared. This is 1/2. Now there are 4 triangles, so 9 minus 4 triangles times the area of 1 triangle, which is 1/2. This is 2, so 9 minus 2 is our area, which is 7.